but also I have to have a scalar function. The scalar function is a number, right? So basically, this is a pretty natural question here. You have a curve right here, right? So RT defines a curve. At any given point on this curve, according to the scalar function, there's a value or a number at this point. All right? So if I change smoothly on this curve, if I move the points together, the function value will also be changed. So the line integral is basically the sum over this whole number, the whole function values according to the smooth curve. Are you with me? So this is a pretty natural question to ask. If you have a curve, at this curve, every single point of the curve, there's a corresponding function value according to a scalar function. And if I want to sum up all these function values on the curves when I move the points together, this is going to be the line integral here. Okay? So the line integral of a scalar function according to a smooth curve is defined by the following. Okay, so this is the formula. Again, it's a one-dimensional integral. I'm just integrating this with respect to p, nothing fancy here. But I'm integrating this with two components. One component comes from the scalar function. I have x, y as the input of x. Now x and y are both defined as a function of t on the curve. So naturally, I want to switch between x to t. All right? And then, because it is with respect to a smooth curve, I have to take the arc length component into consideration. All right? So I have to take the arc length into the consideration. So this is the line integral of a scalar function with respect to a curve. And most importantly, you get a number. So line integral of a scalar function with respect to a curve, you have to have a number in the end. Okay? You have to have a number in the end. So for instance, I can give one example here with respect to this curve. If I have a function right here, I want to compute the line integral of this function with respect to a scalar function, let's see, fx is equal to x divided by x squared plus y squared. So I want to compute the line integral of c, where c is defined as the function straight line going from 1, to 26, fxy dx. So this is the notation for a line integral. Okay, so I should be writing this right here. C means a curve. Scalar function with respect to the arc length component. Okay, so I want to compute this line integral of a scalar function with respect to this piece of straight line we just defined. Okay, so according to the formula, what should we do? According to the formula, because we already have the vector definition of this straight line, it's nothing but from 1 to 26, I have to replace everything by t. X is equal to t, y is equal to t as well, so t squared plus t squared. And then I need to take the arc length component, which is square root of x prime plus y prime. Okay, right? So this is basically my x t. This is basically my y t. So this factor is nothing but the length factor of the derivative. All right? Are you with me? So you have to be on board on what I'm doing here. So I need to take x prime, which is equal to 1, and y prime is equal to 1 as well. So basically here I get a 1 squared plus 1 squared dt. That's the only thing we need to do. You need to plug in t for x and y, and then there is one factor here as the arc length vector. Okay? So this factor is coming from the arc length of the vector function. So this is the x prime squared, y prime squared. So in the end, I'm getting integral from 1 to 26, square root of 2 divided by 2t. All right? So that's about it. So it's 2t squared and t and dt. So in the end, I get square root of 2 divided by 2. 1 over t, the antiderivative is log, so the log 26 minus log 1, I'm getting log 26. That's it. And in the end, you're supposed to get a number. You're supposed to level.
I have two questions. The first one, how did you get the limits? Is it related to the same problem that we did before, or?
There's no limit involved here.
No, like 1 to the 26.
Oh, 1 to 26 is coming from here.
And how did we know these two are related?
Oh, I'm actually computing this line integral with respect to the curve we found before.
Oh, okay.
Okay, so this C is not some arbitrary curve. Right. I'm actually combining these two problems together. We found this curve, we found this parametric form, which is defined by t goes from 1 to 26. With respect to this curve, I want to compute the line integral here. Okay, sorry, I'm confusing here. I want to compute the line integral with respect to this curve. Okay, that's why I'm using these parametric forms as well as the initial time and the terminal time. Second question.
So the answer, that number, what is like?
Okay, so this guy is equal to square root of 2 divided by 2. Ln of t evaluated from 1 to 26.
Yeah, the value of, like the answer, what did it mean?
The answer is this guy.
Yeah. What is it? Like, what is it?
Well, log of 26 is about
No, like I don't
3 times
mean the
something.
actual number. Like what
this
is
is
it?
the actual number.
I know.
What does that
What is it,
describe?
like,
What does that
does it mean
describe?
to me?
Oh, this what is represent? That's a very good question. That's a very good question. So one thing you can understand is if I have this intermediate function to be equal to 1, constant 1, I will be getting exactly arc length. That with me? If I have this intermediate function as constant 1, this is going to give you the arc length. And this is a general thing. Remember, when we want to compute the area of some region, I'm taking the double integral of the function with respect to constant function 1. The volume, I'm taking the triple integral with constant 1. The arc length, I'm taking the integration with respect to constant 1. If you have this function, not the constant function 1, you have a general function. This is talking about a weighted arc length. Or you can sort of understand this as I would say the weighted arc length is the best explanation you can have. So what it means is if I'm looking at the arc length here, okay? In arc length, basically, if I cut into small pieces, I'm taking the length of these small pieces regarded as a straight line. That's what I'm doing here. Right? And then I'm taking the integral, which is exactly adding these lengths of the small pieces together. If I have a function, I'm getting a weighted arc length right here. Because this length is not exactly the length for this guy, I have to multiply by the function value here. Okay? So there's a weight related to the function. That's one explanation. But a much better explanation, what you will be talking about, I would say it's coming from the following lectures. So this arc length, this line integral of a scalar function with respect to a curve is closely related to the fundamental theory of calculus in R2. Okay? So remember, since Marco is asking here, this will be a pretty interesting to think about. So fundamental theory of calculus is talking about if I take in the integral in an interval, I'm getting the difference between the boundary points. All right? So basically, I take the integral in the interior of the interval, I'm getting the difference of its antiderivative function on the boundary. So a very general theme of fundamental theory of calculus is the relation between the interior and the boundary. Okay? That's the general theme of fundamental theory of calculus. In double integral, if I have a region in here, the double integral will be the connection between a double integral in the interior and the line integral on the boundary. So I have to know what the line integral is. So a better explanation of what this number is about. This number will represent the relation between the double integral in the interior and what is supposed to be on the boundary. And that object on the boundary has to be a line integral. Understand? So line integral of a scalar function is related to scalar. fundamental theory of calculus in R2. So one more thing I want to mention before we go. All this calculation works equally well in R3. All this calculation works equally well in R3, which means if I have a curve which is defined by xt, yt, and zt, where t goes from A to B, this curve is going to lie in R3. I should be able to use a very similar formula to compute its arc length by adding a z prime right here. All right? And if I have a scalar function with respect to curve in R3, I have to have a vector field related to x component, y component, and z component. All right? And in order to do this line integral, I just need to replace x, y, z by t and adding this extra factor again. Okay? So all those computations should work equally well for R3. Okay? So I still have a couple of copies of tests here, and I did a lot of remarks in the test. If I want to see you afterwards, so please ask my